Hey, Mike, uh, can you hear me?
I'm looking down at the top of your head, buddy.
We can't hear him. We can't hear Mike. And Mike, I was just going to sort out the sound. Okay, how about now?
Yeah, I can hear you. Yeah, can you hear me?
Yes, yeah.
Okay, hold on. Okay, how about now? Now, Mikey?
Yeah. Can you say
Okay,
my
we
me?
can hear you. We can hear you. Okay. Okay, magic. Right. We're just sorting out the stuff here. There it is. There it is. Look, boom. Oh. We need the mouse. Okay. There we go. There we go. Okay. Okay, we can see you, Mike.
Good.
And we can hear you.
Even better.
And let's just check if the share screen works.
Oh, definitely not that one.
And we've got people in the waiting room. There we go.
Can you see my screen?
We can see your screen. Excellent. Okay. Okay, awesome. Okay, Mike, we're just going to wait a few minutes and then we'll get going. Okay, okay. Okay, we'll just wait a couple more minutes. Huh? Okay. Okay. Okay, we've got some people in the waiting room. Okay, I think let's start. Okay. Teresa just made it. Okay, and we'll decline the AI thing, eh? Okay, okay, guys. So I'd just like to introduce Mike for the Geotalk today. So Mike is uh, professor at Purdue, but he started off doing his undergrad in New Jersey at Princeton, and then went on to MIT to do his PhD with Sam Byring, working on essentially high precision zircon dating. And I think, Mike, I don't think you've ever dated anything else other than zircon, I believe. But and then Mike went to do he went back to Princeton to do a postdoc, and that's where I met him, and we've worked on a number of cool things together, and yeah, and then Mike went on to Purdue to start a job at Purdue, and he's got he runs a Tim's lab there at Purdue, and Mike's actually has family from South Africa, from Johannesburg. So I'm continuously trying to convince him to come and do to bring the family back to Joburg to do a sabbatical, but he hasn't agreed yet. But we'll have to put more pressure on him. Okay, without further ado, please go ahead, and I think you'll be talking about these are rocks from Northwest US, which Mike has up there. So great. Okay, Mike, thanks a lot.
Yep. All right. So you guys, everyone can hear me all right?
Yes, we can hear you great.
All right. Yeah. So please don't hesitate to interrupt me if something goes wrong or if I'm not making sense. So yeah, this is really cool. I love that we have this technology now where we can, talk half a world apart, which is really fun. And yeah, so today I'll talk a little bit about the research that I've done and own petrologic stuff. Let's see. I'm getting a little feedback. Is that messing up the audio? Maybe you can
It
mute.
sounds fine to us, Mike. It sounds totally fine to us. Okay, I'm going to mute our side, which is this one.
All right. Yep. All right, cool. Yeah, so just interrupt me if something comes up. But yeah, today I'm going to talk a little bit about the research that I do that's more, I guess, petrology focused, which is thinking about whether we can use silicic sort of granitoid intrusions to learn about, say, magma reservoir processes. And so, what I want to convince you of, hopefully by the end of the talk, is that when you go out to a place like in this picture on the title slide, where you have an ocean of granite, you can actually learn something about short time scale processes that might be happening in a magma chamber or reservoir. All right. So, just to give you a quick outline, a big focus of this talk is going to be on how do you produce high silica rhyolite and can you link it to plutonic bodies. So we'll quickly cover what is high silica rhyolite. Many of you probably are very familiar with that. Then we'll go into what I call the problem of the missing plutons, which is we have a very nice petrologic model for how you produce these high silica rhyolites, and they should require complementary plutons. And yet, most of the granitoid plutons that we see don't look like they could have sourced at least large volume rhyolitic eruptions. Then I'll take you through two field locations where I think we've solved or found a couple of these intrusions that would fit the bill for a fossil magma reservoir. One is in the state of Washington in the northwestern part of the US, and the other is in the southwestern part of the US in the state called Nevada. So then we'll do some take-home messages, and then if I have time, I'll talk about some new research where we're trying to understand how common are large volume silicic magma reservoirs. So just before moving on, I'll talk about a few of the collaborators for this research. There was Travis Steiner Leach, who's now working for the US government at a national lab, but he was a graduate student at Princeton when we were doing most of this. Blair Shaney, professor at Princeton, Bob Miller, professor at San Jose State University, Ayla Pamukchu, professor at Stanford, Akshay Mehra, professor at the University of Washington, and Tisha Okai, who was one of my first graduate students, who's now at the University of Oregon. All right, so what is rhyolite? So we'll pretend that we're in introductory geology right now. So rhyolite is defined as a high silica magma. So it usually is defined as having more than 69 weight percent silica. It has a very high viscosity. So many millions or billions higher times viscosity than water. Typically, these things are frequently saturated with a gas phase, which creates bubbles. So in this image of a pumice, you can see lots of little vesicles in there. Each one of those would represent a trapped gas bubble. And because it has this high viscosity and it's frequently saturated with a gas phase, creating bubbles, you end up with a situation where you can have explosive eruptions. And so, as a society, we're very interested in understanding, well, what is the source for these rhyolitic eruptions? And if we understand what the source is, can we better predict when they're going to happen? So as an example, this is the Chaiten volcano down in Chile. It erupted rhyolite in 2008. And you can see a variety of hazards here. There's pyroclastic flows going down the side of the volcano. So you can imagine if you were a village at the bottom, you wouldn't want to become a modern day Pompeii. It's also putting in a ton of ash into the atmosphere. And as we all know, ash can get into jet engines and cause them to fail. And so a lot of our modern travel infrastructure can be disrupted by these volcanoes. So we really want to know what's happening underground, where are these eruptions sourced, and how can we leverage that information to better predict when eruptions might happen. All right, so the traditional model for how you would make silicic magmas is that you would have mantle-derived melts, so basalts, come in from below the crust, pool at the base of the crust, differentiate and crystallize, move into the middle and maybe even upper crust, trigger some crustal melting, generating more intermediate magmas like tonalites and granodiorites. And then at the very top of the crustal column, you would end up with more silicic intrusions and silicic melts that could go on to crystallize granodiorites or granite. And it's pretty important that in this little cartoon diagram that we're showing, that the silica content increases as you go up through the crust. And there's a good petrologic reason for that. That is sort of the driver behind a lot of the stuff that I'm going to talk about this afternoon. All right. And so that petrologic reason can be summed up in this ternary phase diagram. So as much as I want to tell you that I'm a good petrologist, I mostly look at rocks that have three minerals in them: plagioclase, K-spar, and quartz. This is basically what makes up a granite. And since granites are a fairly simple mineralogic system, we have done tons and tons of experiments seeing how different proportions of plagioclase are shown as albite on this diagram, K-spar shown as orthoclase, and quartz up here. We've done tons of experiments where we've taken different mixtures of these three minerals and melted them at different temperatures, different pressures, and seen at what conditions different minerals crystallize. And so we're able to build these phase diagrams. All right, and so the way you would read this is if we had a bulk composition that was about that was the composition of the star. As it cooled, it would first saturate with plagioclase and crystallize, and the melt would move in this direction, the melt composition. It would hit this cotectic, the other feldspar, K-spar would join, and then the melt composition would move down this cotectic, and ultimately it would end up at this place called the eutectic, where the temperature and composition of the melt is fixed, and you are crystallizing all three phases, plage, K-spar, and quartz, until the rock is fully solidified. Okay. And so this eutectic is really important because it is very pressure sensitive, and it basically governs how silicic a melt can get. So most natural magmas, if we plotted them on this ternary diagram, we plot down here close to the plagioclase corner. And if that's the case, then the highest silica content that melt could ever get is going to be governed by the point of this eutectic. And the eutectic is very pressure sensitive, such that it is down here, closer to the feldspar portion of the ternary diagram at 1 GPa, or the base of the crust, and closer to the quartz apex of this diagram as you get to 0.2, 0.1 GPa. And so you can actually take the silica content of the expected melt composition at these eutectic points, and you can plot them versus pressure, which is shown here as this black line. Okay. And so high silica rhyolites, things that are, say, greater than 75 weight percent silica, can only be produced in the uppermost crust because of these phase relationships. Okay. And so this petrologic model basically leads to a model of high silica rhyolite systems where you take a intermediate melt, you accumulate a fair bit in the upper crust where the pressure is low. It crystallizes enough to reach the eutectic-like point, or the minimum point in that phase diagram. And then the remaining melt can segregate to the top of the magma reservoir and form an eruptible cap of rhyolite. And so if you look at many textbooks that talk about rhyolitic eruptions, this is the sort of diagram that you would see trying to explain their source. All right, and that segregation also makes some important predictions, in that most of the processes through which we think it happens are gravitationally driven. So you're either accumulating early formed crystals through gravitational settling, or changing the relative amount of early formed crystals and residual melt through compaction. So either way, at the top of the magma reservoir, you'd have this clarified liquid, and at the bottom, you'd have an accumulation of early formed crystals, right? So it's gravitationally driven, so we should be able to see these great compositional gradients between the paleo top and the paleo bottom of the magma reservoir. All right, so these models make very specific predictions for what we should see in the geologic record. Okay, so if you are going to make, say, a large volume of high silica rhyolite, you need a large volume of intermediate melt to have accumulated and contained melt simultaneously over a wide region. You can't sink crystals through something that is solid, and you can't compact and squeeze out residual melt from something that has no melt. All right, so the whole area needs to have contained melt simultaneously. Since the melt segregation processes are gravitationally driven, we should end up with geochemical gradients between paleo up, where you have mostly residual melt, and paleo down, where you should have mostly accumulated early formed crystals. And then all of this, in order to satisfy the petrologic constraints, should happen in the upper crust, all right? So that the granitic minimum will allow you to get high silica rhyolite. All right. And this kind of brings us to what I would call the problem of the missing plutons. So if we go back to those predictions, we should be able to go out into the geologic record and find granitoid plutons that all contained melt simultaneously. So in that sense, we should be able to take different samples of granite from throughout the body and date it and see that minerals that were crystallizing for the melt are all the same age. We should be able to see compositional gradients. So if we go to paleo up and paleo down, we should be able to see signatures of segregated melt and accumulated crystals, and all this should be happening in the upper crust. And so at first blush, this doesn't seem like it should be much of a problem because, as many of you know, if you go out into the Earth's upper crust and you look at the igneous rocks that are there, we have plenty of granitoids out there. So it shouldn't be that hard to find things that satisfy these conditions. However, in the last 20 years, we've gotten more and more precise at making geochronologic measurements. And what we've started to realize is that if we date different hand samples from an individual intrusion and we try to determine whether they are independent in time or overlap in time, we end up with something that is like a one-to-one line. All right, so what this graph means is basically every time we take a sample of a granitoid and we apply high precision geochronology, we get a different date. And so we infer that most of these granitoids are constructed incrementally from many small increments. And it seems like very rarely are they mixing together to make a large reservoir, right? So already we're missing one of the predictions from our petrologic model. Also, folks have gone out to try and look for compositional gradients in granitoids. So this was a PhD project for somebody who was a rock climber, and it must have been like the coolest PhD project for him ever. But basically, he went up to this cliff in Yosemite. So this is out in California in the US. It's called El Capitan. It's very famous amongst the climbing communities. He climbed every single route and took samples from different elevations, and then got whole rock geochemical measurements from them. And so here on the right side of this diagram, I just am showing his data. We're showing silica versus elevation on LCAP. And there's really no geochemical trends there. All right, so we're not seeing evidence of geochemical stratification when people go out and try and look for it. And then finally, if we take this to a global scale and we look at all volcanic rocks and compare them to all plutonic rocks, it seems like at the high silica end, both in volcanic arcs and in rifts, there's not a big difference in volcanic and plutonic compositions. All right, and so what this means is we're not necessarily seeing a cumulate signature, so an accumulation of those early formed crystals when we look at the whole global data set. All right, so we have this very nice petrologic model. We've done all these experiments going back to Bowen to understand how granitoid systems behave that suggests this is how you should be able to make high silica rhyolite. And yet, when we go to look for what should be the remnants of these systems in the granitoid record, we can't find things that satisfy the predictions. All right, so we have this problem of the missing plutons. All right, so over the last, Oh man, over the last like 16 years now. Geez, time is going by fast, guys. But over the last 16 years, I've been working on two locations where we think that we have documented things that are fossil magma reservoirs and granitoid systems. So one is up here in the northwestern part of the United States, right up next to Canada. It's this star here. It's called the Golden Horn Batholith. And one is in the southwestern part of the U.S., close to Mexico, and that's called the Searchlight Pluton. And so I'll walk you through those two areas for the rest of the talk. All right. So the Golden Horn Batholith, it's a Eocene intrusion in the state of Washington. I originally started working there because we were studying a tectonic problem. So we were studying this process called ridge subduction and triple junction migration, where we thought that the volcanic arc up here might end up with odd granitoid compositions. And so the Golden Horn Batholith is particularly weird for a um, Cenozoic granitoid intrusion because it has peralkaline granite and Rapakivi granite in it. So these are things that we rarely see in Cenozoic arcs. And so we thought this would be a great place to see whether this lined up in time with our proposed tectonic scenario. And so I went out as a graduate student and spent several years mapping this Pluton to break out all these different units, and was very surprised in that some of them are quite large, like this pink unit here, which is the Rapakivi phase. And so this area was really fun to map. So it's has a tremendous amount of topographic relief, which allows us to have amazing three-dimensional control on these intrusions. So here's a picture of an area that is maybe has too good of topographic relief. Like obviously I wasn't rock climbing up these faces, but most of these places you can kind of get around and get on the ridges and get a good three-dimensional control on these map units. So to give you an example of what this sort of fieldwork looked like, there's a road running through this valley, and what we'd do is we'd park the car, we'd climb one of these mountains to get vertical control, we'd walk the ridge laterally, and then come back down to get another vertical control. And that allowed us to really map this thing really, really well. All right. And so the beauty of all this is, one, the granitoids were very distinctive, so they were easy to map. I could just walk along and tell whether feldspars were rimmed or not rimmed to see whether it was the Rapakivi granite. And for the peralkaline granite, there were these bright blue sodic amphiboles, so like very easy to distinguish all these things. They also had a very simple geometry wherein they were all sills or sill-like complexes where they're basically lying fairly flat, which you can see in this cross section at the bottom. And so this combination of having flat-lying sills and great vertical control allowed us to get volumetric constraints on each of these map units, which I'm showing here. All right. And this is pretty rare for granitoid intrusions. Usually you don't have a ton of topographic relief, and so you are limited to a two-dimensional map surface. So having this nearly 2 kilometers of vertical relief allowed us to get these volumetric estimates. And so the idea that crept into our brain after we mapped this was one, some of these units were quite big. So the Rapakivi granite is more than 400 cubic kilometers in terms of volume. And so we thought this might be a great location to try and quantify magma emplacement rates, since we did have that 3D vertical control. To do that, we used zircon uranium lead geochronology. So zircon is ubiquitous in granites. It is the perfect little chronometer in that it incorporates uranium when it crystallizes, and excludes lead. So you basically soak up all the parent nuclide and exclude all the daughter nuclide as it forms. So a really ideal chronometer. And then, even better, after it crystallizes and the uranium starts to decay to lead, lead diffusion is negligible unless the zircon has a ton of radiation damage. All right, so for something of Eocene age, like I'm working with here, there hasn't been quite enough time for it to have a ton of radiation damage, and so most of these zircons, the diffusion of lead out of the crystal is going to be negligible or something that we can assume is not there, particularly with the way we treat them. Obviously, if you guys go out your back door and pick up some Archean rocks, the story might be very different with those zircon. All right, and then the last thing is, since we know the decay constants for uranium, 235 and 238, we can use the uranium-lead isotopic composition to calculate the crystallization age of this mineral using a variety of methods. So the particular brand of zircon geochronology that I use is called chemical abrasion, isotope dilution, thermal ionization, mass spectrometry, which is a real mouthful. But basically what we do is we do this process called chemical abrasion, which will dissolve any part of the crystal that has had significant radiation damage prior to analyzing the grain. The way we do this is we anneal the grain at 900 degrees for several days. And areas that have a ton of radiation damage recrystallize into the component oxides of zircon, so quartz and bdelliite. We then partially digest the mineral. Both quartz and bdelliite are much more soluble in hydrofluoric acid than zircon, and so they're the first things to dissolve. All right, so we get rid of those. So any part of the grain that had radiation damage and could have had open system behavior is now gone. Each zircon then gets its own special little bath. So it gets rinsed quite a few times to get rid of all the solution from that partial digestion. We then put in fresh hydrofluoric acid and synthetic uranium and lead isotopes. That's called our spike. We dissolve what is left completely, and then we use anion exchange resin to purify the uranium and lead for analysis on our mass spectrometer. We can also collect all the other elements that were in that remaining zircon that we can then analyze by ICP-MS, and I'll talk about that towards the end of this talk. All right, so the advantage of doing this sort of geochronology is that we get higher precision measurements, so usually better than 0.1% uncertainty, but typically we're talking about 3 to 4 hours of labor per grain. And so if you think about other systems like laser ablation, ICP-MS systems, or SIMS, where you can date an individual zircon in seconds to minutes. This is quite slow, but we get several orders of magnitude better precision. So for example, here's a Miocene sample, and our uncertainties are on the order of tens of thousands to maybe a little bit over 100,000 years. All right, so we can use this sort of high precision measurement to answer very specific questions that require high temporal resolution. All right, so back to the Golden Horn batholith. I went around during my PhD and collected samples to date. All the locations are shown with these yellow circles, so sort of spread out throughout the intrusion. Here is the data that we got out of it. So the 206, 238 date is on the y-axis. Each one of these little colored bars is an individual zircon that was dated. Each little cluster of bars is an individual hand sample, and then the color corresponds to the map, so they're all the different map units. And the The things that were surprising is one, the total emplacement duration for the intrusion was under 1 million years. So this was fairly fast compared to a lot of granitoid plutons that had been studied. But then more importantly, the pink unit, which was the most volumetrically significant of the map units we found, I could not find a zircon in it from across the whole thing that was statistically distinguishable from every other zircon. So every zircon I dated from throughout that whole thing was identical in age. We could then use this information to calculate magma emplacement rates. And what was cool about this is that the magma emplacement rates in cubic kilometers per year were the first ones ever documented in a granitoid intrusion that could correspond to those needed to make large magma chambers in thermal models. So when people do sort of computational models using conductive heat loss to try and understand construction of granitoid intrusions. All right, so this seemed like the perfect place to then look for the other signatures of a fossil magma reservoir, because everywhere that we go into this Rapakivi granite and we date it, we see that zircon was the same age, and so that zircon crystallized from melt, and so the whole area had to contain melt simultaneously. So now we can look for compositional gradients and confirm that this is an upper crustal intrusion. So to look for compositional gradients, I went to the location where there was the greatest topographic relief within that sill and collected a bunch of samples to do whole rock geochemistry. Since this is a coarse grained granite, each sample to get meaningful whole rock geochemistry needs to be quite big. And so I was going up and collecting like beach ball sized blocks of granite to carry back down to the car. And so these 10 samples or however many there are here represented quite a few times of climbing this mountain. And I got in tremendously good shape carrying all these down. All right. So to put this all in a strat column, here's the elevation of this mountain. There was some textural difference in that the closer to the top, the intrusion was a little bit more porphyritic, and then towards the bottom, it was more, say, equigranular. Here's some of the data. So I've plotted two elements that are incompatible, rubidium and hafnium. And so they should stay in any residual melt in a magma reservoir. And two elements that are very compatible in feldspars, barium and strontium, that should be enriched in early formed, early crystallized feldspar. All right, and we do see compositional gradients with elevation. The incompatible elements are more enriched at the highest elevations. The compatible elements are most enriched at the low elevations, so at the bottom of the sill. You can also see this in the rare earth elements, which are generally incompatible. So the colors represent elevation here. You can see lower elevation, we have lower rare earth element content, higher elevation, higher rare earth element content. The exception, of course, is europium, which can go in plagioclase, and so it would act as a compatible element, and you see the exact opposite trend. Higher elevation, lower europium, lower elevation, higher europium. So all these elements are behaving in such a way that it looks like we have a geochemically stratified fossil magma reservoir. All right. Then to confirm that it is upper crustal in origin, we were able to do aluminum and hornblende barometry. I was very lucky in that I was able to get a nice location in one of the samples where all the many minerals that are required in the aluminum and hornblende assemblage were present. And so that's shown here. And then our barometry estimates are shown here, which placed it at, let's say, 0.25 GPa. And this makes sense because if I plot our Rapakivi granite compositions on the quartz albite orthoclase ternary, they make an array, and the upper end of the array is pointing towards, say, 0.25 GPa minimum composition. And the lower end of the array is pointing towards plagioclase-rich rocks, which could represent, let's say, a cumulate. All right, so we had compositional gradients. It's in the upper crust. This looks like it satisfies all the requirements to be a fossil magma reservoir. So another question we had was, could we identify the early formed crystals and late formed crystals texturally? And so we took a really simple approach where we just assumed that the earliest formed crystals are going to be big and the later formed crystals would be small. So obviously this is neglecting things like add cumulate growth, but you'll see why we think this kind of works here in a moment. All right, to do this, we use this instrument at Princeton University called the grinder. It is a serial grinding machine. And so basically you put a slab of rock on it. It'll grind 30 microns off. It will take a high resolution image. It will then grind another 30 microns off, take a high resolution image, so on and so forth. And this instrument was designed and managed by a good friend of both Scott's and mine, Akshay Mehra, who's now a professor at the University of Washington. And it was designed to study fossils and reconstruct fossil organisms, but I was able to convince Akshay that we should do some granites on it. All right, so once you get this stack of images, you then have to train the computer to classify different minerals. And so all we did was we trained it to classify potassium feldspar, plagioclase, quartz, and then we just lumped all dark minerals together as mafics. All right, and so the way we did this is Akshay had me sit down and trace a bunch of these minerals on different images, and then we trained the computer off that training set, and eventually we got to a place where it could auto-classify these things. All right, and so at the end, this is what the data looks like. We get a 3D reconstruction of the rock. So here is a reconstruction where I'm just showing the quartz grains that we have identified within a block that is several centimeters by several centimeters in size. All right, and so what we did, very, again, simple approach, is we took the grains, we sorted them by volume, and we said, okay, where if we have 99% of the smallest grains, so basically the whole rock minus just the 1% largest grains, where would they plot? All right, so 99% smallest grains plots here on this quartz albite orthoclase ternary, and then the corresponding large fraction would plot here. So we did this by getting more and more selective, so fewer and fewer of the smaller grains, and we get to the granitic minimum around when we are selecting 50 to 60% of the smallest grains. All right, and so if this represents late stage melt that crystallized, we might expect that the porosity in this sample of early formed crystals to residual melt that we are recording when the geochemical gradient formed was something like 50 to 60% melt, which is about when we'd expect differentiation to occur, because you can no longer have convection at that crystallinity, but you haven't quite locked up the system. All right, so what did we learn from the Golden Horn batholith? High density geochronologic sampling can identify these fossil silicic magma reservoirs. I think we didn't identify them earlier because we just weren't sampling dense enough. Fossil magma reservoirs can preserve geochemical gradients relative to paleovertical, and these gradients are consistent with gravitational differentiation. And then textural studies may help constrain parameters such as melt percentage that would allow us to talk to, say, the seismologists that are monitoring active volcanoes. So if I'm able to tell seismologists, well, we think differentiation is probably happening when there's 60% melt in a reservoir. That might be a more tight target for them when they're looking at their seismic data. All right, so that's the Golden Horn batholith. I'll try and go through the Searchlight Pluton really quickly, and we'll see if I have time to go through the last little bit. All right, so the Searchlight Pluton is very interesting. So it's in a part of the United States that has experienced extreme tectonic extension. And it is a volcano where it has basically been sliced in half by a low angle normal fault and then pulled up and laid out on its side. And so that's represented here in this cartoon at the top. And so all this happened during the Miocene, so not that long ago. And so there's a 13-kilometer thick crustal section. So you can stand here and walk to the west, and you basically go through the entire upper crust. And this area is cool because it includes both volcanic and plutonic rocks from the same system. So if you look at it from a satellite image, now we're not in majestic snow-capped mountains, but we are in a desert. The Colorado River, which is all dammed up, is this dark thing on the right side of the image. But the 13-kilometer crustal section runs through here. And it's in the very southern tip of Nevada, so south of Las Vegas. All right, and so for a long time, this has been considered a classic differentiated granitoid pluton, because if we just make a simple cross-section of it, it's got sort of lower silica lower part, lower silica top part, which are supposed to represent cumulates at the base and a roof solidification front, and then a granitoid in the middle, which is even capped with high silica granite in this sort of dark pink color. But we've known since the first papers were published about this that the whole intrusion probably wasn't placed over a couple million years. And so that initial call that it was a classic differentiated magma chamber is probably wrong. However, what we were able to do is we took samples from just throughout the granitoid part, which is a few kilometer thick sill, and we were able to show again that in all these samples, the dates were more or less identical. And so this thing contained melt throughout it simultaneously, all at the same time. So we can go back through the same conditions that we talked about earlier. Can we see a geochemical gradient? And we know it was in the upper crust because of geometrical relationships there. All right, so to look for geochemical gradients, we decided to do a vertical transect through it along paleovertical, same as the Golden Horn. So over here on the right is just silica content versus relative depth within the pluton. All the black samples are previous samples. All the yellow samples are things that we dated. And we got really interested in this middle pluton because it shows this gradient in silica content. And so I started to get this idea that perhaps if we had more detailed knowledge of what that geochemical gradient looked like, we could learn something about what processes were governing differentiation. All right, so if you imagine a magma coming in, you're creating a magma reservoir. At low degrees of crystallinity, the magma can convect, and so crystals will stay suspended in the convecting magma. Close to the point of rheological lockup, you go through this brief window where they can either settle or compact. And so the idea was the geochemical gradient, which basically is telling us something about the paleoporosity or amount of residual melt in a sample, could tell us about these different processes. So for example, if there's no relative movement of crystals and residual melt, we would see no change in compatible and incompatible element concentrations through a vertical section of the sill. If we settle, you're basically going to settle these early formed crystals onto the bottom of the magma reservoir, have clarified melt on top. The settled crystals will end up achieving the closest packing configuration that they can. And so you would end up with a step change in compatible and incompatible elements. If it was compaction, you would have a gradient in paleoporosity through the whole thing. And so you might expect smooth changes in compatible and incompatible elements with constant concentrations in the segregated melt at the top. And so I wanted to get these gradients. I wanted to have a much higher density geochemical set of measurements. And so I thought, well, let's use a portable XRF and see if we can do this um, more efficiently than collecting all these samples and doing traditional whole rock analyses. And so here on the right, I'm showing the position of all of our um, uh, portable XRF and more traditional ICP-MS analyses for whole rock measurements through this stratigraphic column. All right, so in order to do portable XRF well, you need to calibrate it. So we spent a lot of time calibrating it with different granitoid samples. And then you need to quantify how reproducible it is. So basically what I'd do is I would take this thing, and to make sure that I was integrating a large enough volume of granite to get meaningful data, I would sit down with a block of granite with known composition, and I would analyze it for like 30 minutes in a bunch of different spots. And then we'd take a mean. And so that would give us, say, one of these points or one of these measurements. All right. So I could do that a bunch of times. I could get a calibration curve that way. And then every day when we were out in the field, at the end of the day, I would sit down and analyze another block of known composition that was not on the calibration curve to see how variable my results were. All right. And so this shows for barium that we were getting about 10% variability. And so in the end, I really only trusted a few of the trace element measurements from this instrument because the variability was so high for most elements. And if I were to do this again, I think I would do it using traditional whole rock. But you know, you gotta try new things sometimes. So we tried. Okay, so here are the geochemical gradients we got. So rubidium, which is a incompatible element, again, in the pink unit where everything is the same age, it increases up section. Strontium, which is a compatible element, is basically constant and low at the top where we have leucogranite, so the highest silica stuff, what is probably segregated melt. There's a somewhat linear change below that, and then another constant uh, uh, composition or concentration of strontium low in that sill. And then what's really cool is there's this big compositional break right at an intrusive boundary here, which I think is cool that we were able to catch that. All right, so if we look at that strontium curve and we go back to what I had proposed, which is that the shape of these curves can tell us something about process. It looks like we had a constant porosity at the bottom of the sill. So here we could interpret this as a zone where the crystals had reconfigured to the point where they were in their closest packed configuration that they could get. And so you end up with the same amount of residual melt and ultimately the same strontium concentration throughout that zone. There is then a zone where clearly there's mixing or a changing porosity where you have lower porosity, lower amounts of residual melt at the bottom, higher amounts at the top. We think of this as a zone where crystals are settling and then reconfiguring through some sort of like loose compaction, not viscous compaction, but just reconfiguring their position to achieve that closest packing positions. So sort of like a compaction zone and then clarified melt at the top. And so we think we've learned maybe something about the processes through which um, uh, these high silica melts are clarified. All right. And so from this, we can get the magmatic conditions during differentiation. We know that the magma had reached the granitic minimum because the residual melt has a minimum composition. And we also know that crystallinity was low enough that gravitational differentiation could still occur, so 20 to 55% crystals. And so just like the Golden Horn batholith, the goal here is to be able to tell people at volcano monitoring sites, hey, if you're estimating from your seismic data that you have uh, something that looks like a silicic magma reservoir underneath the volcano, and it is at 20 to 55% crystals, this is when we'd be most concerned about it differentiating and having an explosive high silica rhyolite eruption. All right, let's see. All right, I got a couple more minutes, so I'll just do differentiation and then I'll cut the last little bit. All right, so we could ask the question, how long did differentiation take? In both cases, we've dated lots and lots of zircons from the units. In the case of the Golden Horn, we have no distinction between individual analyses. They're all statistically the same. And so the maximum duration that is allowable for that still to be the case, given our reported uncertainties, is something like 100,000 years. For the Searchlight, it's younger, so we have a little bit better age resolution. And in this case, there is age dispersion, and we can calculate the minimum amount of time that must be there given our reported uncertainties. And so the minimum duration here is 90,000 years. All right. And so in both cases, it's suggesting that differentiation must have occurred on timescales of 100,000 years or possibly faster. So you could ask, well, you're dissolving whole zircon grains, so are you really getting a representative time estimate? And that is a fair question. And so to try and answer that, we're going to look at the trace elements in the zircons that I dissolved. All right, so here is a diagram that plots titanium relative to hafnium for zircons from this system. So all the dots are things that I measured on a SIMS. Because we can measure titanium on that really well. So these are in situ from grain mounts. And you can see that titanium and hafnium have this nice relationship where high titanium, which corresponds to high temperature zircon crystallization, corresponds to lower hafnium concentrations in the zircon. Low titanium, which corresponds to low temperature, corresponds to higher hafnium concentrations. All right, and then this whole thing flattens out down here where the temperature is likely constant, and this represents the granitic minimum. So once the temperature is held constant, once you hit that minimum in the quartz albite orthoclase system. So this curve here, this dark probability density curve, shows the concentrations of hafnium measured in the zircons that I dated. And you'll notice that they correspond to high all the way down to temperatures that would be consistent with the granitic minimum. They're missing the last little bit of zircon crystallization, but we are capturing the key interval from high temperature, where there's likely very few crystals, down to the granitic minimum, where we think the differentiation action occurred. And so I think the timescales that we've got are meaningful. And so I'm going to wrap it up here. So my conclusions from all the field and analytical work is that we can find plutons that meet the criteria for our predicted petrologic models. We just have to do higher density sampling than we were before. The geochronologic data from our two examples that we discussed here suggests that differentiation occurred in less than 100,000 years. This is consistent with crystal settling and not so much, say, viscous compaction. So actually recrystallizing minerals to compact, that would take much longer. And then I think that there are future avenues for using textural and geochemical data to better constrain sort of what processes were leading to differentiation. And so with that, I'll be quiet and take your questions. And I appreciate you guys having me this morning, afternoon. Oh, Scott, remember you're muted. Yep.
Okay, I'm sorry for struggling with the mute button there. That was a fantastic talk, man. So we really appreciate it. So, and and we were on mute, but the jokes were very good. So that if you didn't hear laughter, that's why. So I don't know if anybody from the audience has questions or from online. A question here from Anton.
Thanks a lot for interesting talk. Just want to ask a very simple question. What is the speed of settling of crystals in this sort of granitic melt? Because they're very viscous. Will, for example, a plagial place with a density of say 2.6 gram per cubic centimeter actually settling fast, given this parameter? Have you calculated this?
Yeah, that's a great question. There's a paper by Olivier Bachmann and George Brigance where they go through sort of hindered settling equations for sort of the expected viscosity of a rhyolitic melt. And when you do that and you do sort of hindered Stokes settling, you get like time scales of going 100, 200, 500 meters of settling in tens of thousands of years. So the time scales that I'm reporting are fine with that.
Okay, so they correspond to the time scale. Okay, thank you.
Okay, Grant, there's a question.
Thanks so much, Mike. It's Grant Bivey here. That was really cool, very, very interesting, and also very different to what we kind of normally think of in terms of high precision geocon in the South African context, which is much more mafic. I was just wondering, from this perspective, the silicic perspective, would you envisage that differentiation time scale to change throughout the crustal section? So if you're dealing with an arc environment, for instance, do you think much deeper in an arc environment, maybe in the mash zone and in the crustal hot zones, do you think you might have much longer timescales of differentiation occurring then? Higher in the crust is much more rapid?
Yes. So, the melt resonance is going to be governed by the ambient crustal temperature. Yeah. And so if you are deeper in the crust, you're going to have a much longer period of melt residence, and other processes like viscous deformation of say a crystalline framework could totally happen on those time scales.
So what some of those timescales could be, like you're saying less than 100,000 years in this upper crustal kind of reservoir, but could we be dealing with 1, 2, 3, 4, 5 million years in the lower crust? What kind of timescales are we thinking about there?
That's a good question. So I'm not familiar, like I would want to run or have, not me, somebody who knows what they're doing would run like thermal models for these lower crustal reservoirs. I think that we can gain some insight from the geologic record in that, like say in an arc, something that fascinates me is that volcanoes are only around for a few million years and then they move. And so my guess would be that that time scale of a few million years is telling you about the time scale of the whole magmatic system, both upper and lower crustal. And so something on the order of a few million years, I think that makes sense to me for deep in the crust. Although, there's nothing stopping deep crustal things from operating quickly as well.
Great talk. When it comes to your rubidium and strontium ratios going up through your profile, was the modal proportions of your feldspars the same going up through the section? Because I guess that would change the compatibility of rubidium and strontium if your proportions of the different feldspars are changing. That being said, we are in a granite system and you may have subsurface alteration from any fluids that come out. Do you see any of that influencing your rubidium strontium ratios as you're going up the profile?
Yeah, good question. So I have not done like trace element analyses on the feldspars, so I can't. I don't have the data to answer that question as to whether the strontium concentration in the cores of the plagioclase is changing up section.
Even in the whole rock, if your modal proportion of K-spar versus something that's calcium rich changes, you'll have a 8% change, I guess, in your rubidium or your strontium, because one will preferentially substitute into K-spar, with the other one will preferentially substitute into your calcium-bearing feldspars.
Oh yeah, so that is definitely true. Like the proportion of plagioclase deeper in these systems is higher, so lower down in the sills. But you know what I would attribute that to is that plagioclase is going to be the first thing to crystallize in the system. So you're going to have more abundant plagioclase early on. So when you say hit that granitic eutectic or minimum point, you're going to have a higher proportion of plagioclase in what is solid at that point.
Michael, thanks so much for your talk. Really enjoyed it. I guess we'll see you in Johannesburg quite soon. In the first case study that you showed, the sort of granitic sills are kind of being placed incrementally. So I'm just wondering if you've got a sense of how you reconcile that with these larger single systems that show nice differentiation trends. How do the two sort of fit together? Are individual bodies all collectively feeding high silicic melt? And then if I can just sort of build on that, if these systems are being placed incrementally, then presumably you can kind of remobilize perhaps already crystallized or nearly completely crystallized intrusions, and therefore sort of tap more of this highly silicious melt as you're sort of building up the Pluton. Thanks.
Okay, so I'll start with the second part about the remobilization. In both the cases that I talked about today, the only areas where like the boundaries between the sills that I discussed and the surrounding rock that were mushy and looked like that contact could have remobilized things are intrusions that were, let's say, less than 50,000 years older than the sill itself. So it seems in both these cases that the geotherm was still cold enough there that melt residence for a lot of these smaller increments was very short. And so we weren't having a lot of interaction, at least amongst what we can see today. To answer your second question, I really wish that I got to reconfigure this talk because the last little bit is tries to answer that question. So can you guys still see my slides?
Yes, yes, we can. Yeah.
Okay, so I'll just really quickly. All right, so there's this thing called the Sadler effect, where if you look at sedimentary rocks sections, the longer you look at it, the lower the apparent rate of sedimentation. All right, and this comes about because it's a very punctuated process. You have like a day where you have a flood and you get a sedimentary bed, and then you have a long hiatus where nothing is happening. And so you integrate all those things together. The hiatuses are so long that the longer you look, the lower the apparent rate. All right, so we decided that this is like more or less the same as incremental Pluton emplacement. And so we plotted apparent rates versus the duration that we see with intrusions that have been dated with high precision, and we get the same sort of relationship that you see in sedimentary systems. Where I'm going with this is that we can then use this relationship and invert it and ask, well, what is the duration of hiatuses? What's the distribution of them? And what is the distribution of increment sizes? Here we use map, so square kilometers. And what you end up with are distributions that look identical to the distribution of eruptive volumes and repose times at volcanoes. So you have lots of little things, lots of short hiatuses, but there are still, you would expect, large events and sometimes very large periods of time between emplacements. And so what I think we are seeing when we see these larger intrusions that we're able to differentiate are the big events. And so I think these are sort of like babies, but the granitic equivalents of like, say, Skaergård or Bushveld, like these things where somehow you very, very, very rapidly assemble melt in a place.
Yeah, great, great. So we've got a question from online. So can you unmute yourself?
Hi, yes, Sue Webb here. I've got a sort of an odd question. How close is the density of the kind of residual melt to the various crystals? And do you ever, are they ever close enough that some of the crystals might float?
So yeah, good question. I have not calculated that. The expectation, and I'm going off of, again, the work that Olivier Bachmann and George Bergantz have done, is that all the stuff will sink. And it will sink at rates of fast enough that you could move it, say, a few hundred meters in tens of thousands of years. But that's a good question. In both cases, I don't see anything in the field that would look like accumulated crystals at the top. The top of both sills looks a lot like just clarified high silica granite. So it looks like the residual melt.
Okay, great, thanks. We see something in the Bushveld, and anyways, I'll talk to you when you come here if you're coming.
Someday, yeah. My family wants that to happen for sure.
Okay, good. Just got one online question, and then I think we'll call it, Mike. But what mafic rock what are the ultramafic rocks associated in the Golden Horn batholith? And that's from Dr. K. Saranya.
I'm sorry, what are the mafic rocks in the Golden Horn?
I mean, I guess, are there any ultramafic rocks associated with the Golden Horn? Is it all kind of involved?
Sir, hi, hello. This is Dr. K. Sharanya. My question is actually you talked about granite Rapagavi rocks, and you are talking about the differentiation also. That's why I asked that question. Any ultramafic occurrence is there, and have you concentrated that also? Have you studied about that also? That is my question.
Yes, thank you. Good question. So, volumetrically, there is not a lot of mafic magma associated with that. There are a bunch of dikes that are sort of like basaltic andesites of similar age. There is a diorite that is part of the complex, but it's volumetrically insignificant. In the Rapakivi granite itself, it's possible that that texture was generated from mixing. I mean, I haven't studied it. If I had to guess, I would guess that the mixing was between two silicic melts and not a mafic and a silicic melt, just to make it more viable. But if mixing generated that texture, the rimmed feldspars, then it had to have happened before we generated these geochemical gradients. And so what we're seeing now would be a thoroughly mixed magma, and then the remaining crystals could have settled out. So yes, I understand that. Yeah, when you see Rapakivi, we tend to think of mixing, but and that certainly could have happened, but the record of it is not present in the data that I have. I think we'd have to get into some more isotopic measurements to get after that.
Okay, sir. Thank you. Thank you so much.
Thank you.
From the room?
Hi, thanks for the talk. I just wanted to ask, so you said that identify the cumulates and residual melt. Like you did not consider the accumulated growth. Can you please elaborate on that a bit?
I missed the last part of that question. I do not consider, what was that?
The accumulated growth.
Oh yeah. Yeah. So we're not considering the accumulate part in the textures because we basically have in that approach we're using just a camera. And so we're very limited in what information we could get. So we could get the size and the composition of each mineral. And by composition, I mean like, is it a plagioclase or a case bar or a quartz? And so it would be very hard for us to using the photograph to determine what is accumulate. So we're just making a simplifying assumption that what is big is early and what is small is late. But yes, we are neglecting that completely, which would mean that we should not put a ton of stock in the sort of residual melt estimate that I showed you. There's some uncertainty there.
Okay, great, Mike. Thanks again. That was a fantastic talk, and let's give him a round of applause, guys. I don't know if you were able to hear that, Mike, but thanks.
It's good to see you, Scott, and thank you for having me. And yeah, it's really cool that we can do these talks all the way around the world.
Excellent. Okay, guys. Thanks. Thanks.